did venture away to Dartmouth to get his undergraduate degree, but since the West Coast is indeed the best coast, he came back here at Berkeley, where he's working on his PhD in environmental science policy and management. Notably, Benji also does stand-up comedy. He is very eager to tell you that he has hazel eyes, and he also, despite going out into the field and hunting and capturing spiders, he's actually afraid of them. So, Benji will now tell you guys a little bit about how spiders perceive their world, and it is super, super cool. So, please enjoy.
Thanks, Ashley, for that introduction. That was all true. And thanks, everybody, for coming out. I hope you find this interesting. I can sense that many of you are excited. See, comedy. You should come to my shows. It's top-notch stuff. Anyway, I'm going to tell you all a little bit. Can everybody hear me with the level that my voice is at? Yes, thank you. So I'm going to tell you a little bit about some of the work I've been doing on spider senses. And please interrupt me a lot, as Ashley said. I know the answer to every question you might want to ask. So, that's not true. That one. Oh, they're hazel. Thanks. I appreciate that. So I'm talking about animal senses, so we have senses. We see stuff and we hear stuff and feel stuff, and so do other animals, but why? What are you doing with all these senses? So senses are only important if you have behaviors, and senses help you do the things you need to do. So you could use your senses to find food. You could use your senses to find shelter or mates or avoid predators. So this is why so different animals have different needs, so they have different senses. I'll give an example. If you think about a hawk, they need to catch really distant prey while on the wing, so their eyes have incredibly high spatial acuity, a lot of megapixels, and they could see really good detail from really far away, and so they could catch their prey. On the other hand, sponges don't do any of that, and sponges just sit around filtering the things that they're in already, and so they don't need fancy eyes or any eyes at all. But but a hawk doesn't have better eyes than a sponge because a hawk is better than a sponge. They just have different needs, so they do different stuff. It's, an animal's senses match their lifestyle. So for a lot of tasks, more than one sense is needed to accomplish it, and this is called multi-modality, when more than one sensory modality is used at a time for a given task. And so one example is trout. Use senses multimodally when they're catching prey. They have different senses. They sense the chemicals from their prey in the water, and they're also able to sense the movement of the water that the prey causes in order to localize them. And they use that information together. So if they're thinking about food, they could use more than one sense to make it happen. My research is wondering if jumping spiders use their senses multimodally in prey capture, or at least that's the research that I'm going to be talking about today. I do some other things with jumping spider senses that I'll touch on, but this is the main thing I'm going to be telling you about. So, any questions so far? I expected to get interrupted way more than this.
What do sponges sense?
That's such a good question. I was wondering, maybe not a lot. Yeah. I know, when I made these slides, I was like, but do they have... They probably, this is me wildly speculating, they probably have some ability of sensing chemicals in the water around them, but they also might not. And I don't know. So how about that? So you might be wondering, especially since the piece of information that Ashley revealed about me, why I'm studying spiders. Well, spiders are super cool. I am only afraid of them because I was born that way. They're awesome. They're not actually, they pose no threat. So A, they're really cool, but B, I'm interested in sensory ecology and evolution, and why And spiders have very cool senses that we know a good amount about. Have I gotten too quiet, or are we good in the back? Cool. So a couple examples. This is an Orb Weaver Spider, classic Charlotte's Web type. Has the ability, the very finely tuned ability to detect substrate-borne vibrations, which are vibrations transmitting through what they're standing on. So it could detect the vibrations in its web to know where its prey is and move to that spot and eat it. Another example of a really cool spider sense is from this net casting spider on the right, also known as an ogre-faced spider, which you may be able to guess why. These spiders have really giant eyes for their size, and those eyes are used for really good night vision, because what they do is they go out at night. Like most spiders are nocturnal, they go out at night, and these spiders, most spiders don't have very good vision at all, actually. But these ogre-faced spiders, they can see in really low light, and then they take these nets that they make and they throw them on their prey, and that's how they catch it. And that's why they call them net casting spiders. Very cool. Anyway.
Which one is bigger eyes, the ogre face or the jumping spiders?
The ogre face has bigger eyes.
Bigger eyes.
Yeah. And then, that's a good question. I'll come back to that. Yeah. Or I wouldn't have, but now that you asked, I'm going to, because it's a good question. And so my study animal is a jumping spider. Jumping spiders also have big eyes, but they're big for different reasons. That also is 2 slides from now, so I'll tell you more about that after I tell you a few other things. Jumping spiders don't have webs. So unlike Charlotte, they just hop around and they jump on their prey. Sometimes I read once that in ancient China, the word for jumping spider was fly tiger, because they're like tigers for flies, which is a cool. I'm into it. And they got stripes on their face, and they jump around, and they stalk their prey. It's a better net. And also, other spiders jump, and other spiders even jump more than jumping spiders do. But so I don't know, whatever. But it's just something.
What fraction, like what percentage of spiders don't use webs? Or like...
Oh, that's a great question. I don't know the percentage, but tarantulas and that whole group don't. And then there's a whole group of spiders that jumping spiders are one member of, which is called the RTA clade, that have, and so it includes wolf spiders and others that all mostly don't use webs to catch, but they all evolved from spiders that do use webs.
Yeah, they abandoned webs rather than...
Yeah. So some, like tarantulas, were pre-web, and these spiders are post-web. Yeah. Is that right? Cool.
Hunting spiders would be the that's, that don't use webs.
Yeah. So a lot of spiders, they go around and they catch what they want instead of waiting for it to come to them. Another thing about jumping spiders that's different from the typical spider is that they are diurnal, so they're active during the day and not during the night. And their eyes, well, so jumping spiders have really cool senses too. They, like Charlotte, they also can detect substrate-borne vibrations in a really sensitive way, even though they're not standing on webs. And also they have fantastic eyes. Their eyes are also huge, although not as big as net casting spiders' eyes, but they are huge for a different reason. So these net casting spiders are out at night, and so they need to see in the dark, and these ones are out during the daytime. And so if you're a big animal like us, you have sort of a lot of room in your eye, so it could be a Swiss Army knife of eyes and do all the things that an eye could do. It could see in really good detail, it could see good color, it could see well at night, or at least decently well at night. But that's because there's enough room to put all the things in that you'll need. But if you're tiny, you sort of have to pick one for the application that you're doing. So the net casting spider's eyes are optimized for seeing in really low light, but they don't have incredible resolution. So the detail is lower, but they have a high sensitivity, so they could pool all the information and get some good low light vision in there. Whereas jumping spider eyes do the opposite. They split things up a lot. And so they try and get as high detail as they can. And their eyes, the front things, are not actually eyeballs. They're eye tubes. So they are super long. So they can't move their eyes around like we can. They just have to move their heads, which is cute. And they also move their retinas, which is cool. Yeah, it's cool. It's very cool. But that part is less cute, but awesome. So they instead of moving the front of their eyes, they move the back of their eyes, actually. So there's a really cool video that I unfortunately don't have to show you guys, but here, you'll get to look through these later. But imagine this is the front of my face. What that's actually going on is it's like this, where the backs of the retinas are moving in order to scan things. And so these eyes, even though they're big, they're like telescopes that have really small fields of view, and they essentially scan what they're looking at. But they need a lot of light to do it. So, also, just so you know, they don't have human eyes and human ears. They have spider eyes. And something called the lyriform organ, which is like ears on their legs for detecting these substrate-borne vibrations. No, yeah, so the different eyes do different things, which is so cool. And also actually has to do with my research methods. So these two big eyes, they're the anterior median eyes, the principal eyes. Those are the ones that are like the telescopes. Those are the really famous eyes from jumping spiders. Those are the ones that see color, and those are the ones that have tiny fields of view, and those are the ones that have like the incredibly detailed vision. And these eyes, these anterior lateral eyes, compared to insects, for example, actually still see really well. Studies show they're primarily used for motion tracking rather than scanning details, so they don't seem to be like looking at the pattern on somebody's face or identifying targets, but it could be used for motion tracking. Or it seems like it's used for motion tracking. And then they also have some backwards facing eyes, and they have some other eyes on the sides of their head that people think don't do anything. Yeah. So they have 4, but 1 pair is sort of vestigial and doesn't really do much. Oh, yeah, so 4 pairs of eyes. Spiders have either 4 or less pairs of eyes generally. So in some groups of spiders, some pairs are lost. Sort of jumping spiders are hopefully lost one of the pairs, sort of. And so... What? Like 3.5 pairs of eyes. Okay, yeah. But not 7, right? Yeah. Maybe 7 if you count each as half. Which I will from now on. It's a lucky number, right? That's why they do it. That's my new hypothesis. So, I'm doing my sound right now. Actually, it's not going to work properly. I'll make this for myself. This is, So I mentioned that we know that they have great vision and they have this vibratory sense, and they do use it, and they are known to use those multimodally. And how we know that is that they use them in making decisions about who to mate with. And the males do these really cool ways to the females where they do a dance and a song. Oh, and And so they do this dance, and they vibrate a song through the ground to the female, and the females are able to feel with their legs and their lyriform organs what song they're singing. And so for those of you who can't hear what's going on, it's like So we don't get these spiders. We don't grow these spiders in the lab. But we go out and catch them, and so we do little expeditions to Lake Berryessa, which is where we catch them. There are many people in the audience who have been on these voyages with me, actually. So thank you all.
Where is that?
This is Lake Berryessa in Napa County, California. So it is. We don't catch them inside the lake itself, but sometimes it floods, and places that I used to catch spiders are underwater at present, which is what it is, I guess. But so this is where I go and I get them. And so I'm going to tell you about a study that I did and then a study that I'm doing. And so yeah.
Is it hard to raise spiders in the lab? Why would it not?
2 reasons. A, yes, it is hard. It is somewhere between hard and not yet possible.
That's pretty good.
Yeah. And the other reason is because if we use wild-caught spiders, it's more. We could be more confident that it more closely approximates what it would be like in the wild. Even though doing a lab experiment, it's never exactly how it would be. It's closer than having ones that had never seen the wilderness of Lake Berryessa. Yeah. Oh, I'm so glad you asked. So we take these little vials and a fanny pack and walk around until we see a spider on the ground. And if you want to know how big a jumping spider is, here's a male and here's a female inside little tubes. I'll pass them around. They're small. They're like half a centimeter. Who wants them? Who wants it first? Yeah, okay, great. Yeah, you raise your hand first. Yeah, so you could pass those around when you're done. So we take these little tubes, we find the spiders, and we say, ooh, there's one. And then we bend over, and then you kind of coax it. You just kind of put it over it, then it jumps into the tube, and then you snap it, and then you put it into a different section in the fanny pack. It's cutting edge.
How many times does the spider jump up your sleeve?
I wear short sleeves when I do it. So, yeah. Oh, I think a spider has gone up my sleeve at some point. I mean, it's happened more than 0 times, but not all the time, because usually I wear short sleeves.
So, you know how some drug dealers will make like different things with their eyes instead of having eyes, so they don't need them, like sexual horns or something. Like, do spiders do that with the eyes they don't need? Do they like make them into like something that they can use for sexual display instead, or you know?
Cool. I don't know any examples of them sort of elaborating their eyes into anything, but in terms of using eyes as sexual displays, so the male jumping spider has to know when to start courting, and a lot of the time just dots representing the eyes of a female are enough for it to start courting. So it does use the eyes to say, oh, that's a jumping spider.
They develop horns instead of eyes sometimes. Like,
Yeah. Yeah. Some spiders def have horns, but not really instead of their eyes, as far as I know. You never know. There's probably some undiscovered species that does exactly that. With animals these days, you can never keep track. With the economy the way that it is. And so, anyway, so what kind of science did I do? Let's find out. The first thing I did was wondering, okay, these jumping spiders, they have these huge eyes. They're using them to evaluate their mates. But they could also detect these vibrations. What are they using to catch their prey? How important is the vision from these how important is their vision in catching prey at all? Do they even need it? Like, I could find my way to the bathroom if the lights are off. Maybe the spiders are able to catch flies without any light.
So what I did was I did experiments where I had a spider and a fly,
It was actually a walk because they were flightless flies, but inside, I don't know how I was acting it out, I have it here, inside of these little arenas, and I saw how long it took them to catch it under different lighting conditions. So what I did was I took this little arena, which is made out of a nylon stocking and a jewelry hoop and a transparency slot with a bunch of goop put on the inside so that they can't climb up the sides. Then I took this device, which is a Kessler removable exposure, which it keep the fly underneath it until it's time to start, and then I pull it up, and then the spider could go and catch the fly, or not catch the fly, depending on the outcome of the trial.
What was that called?
The Kessler removable exposure, named after its inventor. And then I put the whole thing underneath this, which is a tube that used to pour concrete, and some pieces of laser cut plastic, and an aquarium light, and there's a GoPro in there. And so that's how I know what's going on. Take videos of the spiders. This is I'm not going to shine this directly at you, but this is the aquarium light, and I am able to, I use these because I can control the brightness and the color.
Does a different color make a difference?
What?
Does a different color make a difference in what you can see?
So I'm in the process of doing a study on seeing if the different colors make a difference in who they choose to mate with, or how they make their mating decisions. Because if you remember from the, I don't want to perform the keystone correction. Oh, the picture of those male jumping spiders, they had a lot of red patterns on them. And so I did mating experiments where I had just regular white light, or I had light where there was no reds, so those red patterns wouldn't show up. And I'm seeing how that, if that will affect the perceived sexiness of the males, essentially. And so I'm still working on that. I don't know the answer to that, but that I'm also curious. Nobody knows yet, actually. So, but that was the reason why I got the lights, was so I could mess with the colors and see what it's like. But for this one, I tried what I could to keep the colors constant, and I changed the intensity. And so I had bright lights, which were bright enough that I wouldn't want to shine in even their faces. And then I had dim lights, where as dim as it could go while having the same color composition as the bright lights. And then I had totally dark, and I filmed it in infrared like a ghost hunter. What?
Were there any ghosts in there?
There's got to be a lot of fly ghosts, but they didn't show up. Seriously, ghost hunters are so, like, I was on so many ghost hunter forums when I was looking for how to film in infrared, because that is the main market for filming in infrared. Like reading all this, like.
Do you know enough about the eye morphology to know if the spider can see in infrared? It's diurnal, so probably not. But do you know that?
Yeah, so they almost definitely do not see in infrared, but they do see in ultraviolet, which is cool. Yeah. And in fact, seeing in red at all, most spiders we think do not. However, this group of spider in particular seems to have a new eye adaptation to be able to see in red. So even in just regular red, but yeah, probably don't see infrared. But it's normal for spiders to be able to see further into ultraviolet than we do. Yeah, in general, humans have 3 sensitivities to different colors of light that we combine to. Oh yeah.
So what's the benefit of being able to see further into ultraviolet?
I don't know. It might be nothing special. It might be that ultraviolet to them is just purple to us, and then, or just blue to us. It just happens to be where the pigments in their eyes that detect the light happen to be. They have an ultraviolet one and a green one. Basic spiders mostly are thought to have just one ultraviolet and one green, and so then they're colorblind in the same way that a dog is. They could see colors, but not as many as a human could, because they have 2 color channels. And humans typically have 3. So these spiders have 3-ish, so they have the ultraviolet, the green, and then some of the green channels got modified to be like a red one. So people have generally a red, a green, a blue, and then instead they just have a green and an ultraviolet, or a green, ultraviolet, and red. What was I saying? Oh yeah, so so bright, dim, dark, and the dark is just infrared. And then I saw if they could catch a fly or not. And what do you think happened? Any guesses? What happened?
Fly death.
Fly death. But when? What do you think? Okay, so let's see. All right, what are people's guesses for the percentage of flies caught when it was bright? I give them 3 minutes. I put them in the little arena for 3 minutes and saw, could you catch a fly, yes or no? Let me hear like 3 or 4 guesses about the percentage of flies caught in the bright light.
85.
I hear 85, I hear all of them. 60. Okay. How about dim light? What's the percentage that people think?
89.
No, the dim light is about 500 times, or more than 500 times dimmer than the bright light. It's like the light of a full moon. So okay, I hear 0, I hear 89, what else? 50? I feel like I'm in an auctioneer. Okay, dark, what percentage do you think was going on? I hear 0, what else?
80.
0, 80?
20.
0, 80, and 20? Okay, let's see. And boom. This is what happened. Bright, almost 100% of them caught it. Dim, about 3/4 caught the fly. Dark, never, ever, ever did they catch the fly in the dark. This is including a time when I did like a fly party and I had 30 flies and I put the spider in and I waited an hour and it just never caught any of them. And it's not like they went to sleep either. They were hopping around and doing their thing. They just did not catch any flies.
Did it try?
It's hard to say if it tried or not. They were definitely jumping and they jump in order to catch their prey, but I don't know if it was trying to catch. I actually plan on going back and more carefully looking through those videos and trying to see if it looks like they're trying.
Don't you think the spiders is using vibration a lot to catch things? So it means they're like really focused on their vision.
Exactly, yeah. So I was wondering if the vibration could fully compensate for the light and allow them to catch it without any of the light. But it seems that the vision, even if the vibration does also play a role in prey capture, the vision is absolutely essential. And so between the bright and the dim, it looks both like they did pretty well. And in fact, we were surprised to see them do as well as they did in the dim light, considering how dim it was. It's dimmer than you ever see jumping spiders out catching things. In fact, it's dimmer than you see a lot of stuff because it's kind of too dim to see. but this was close to 100%. This is 75%. So there was a difference. There was a decrease in performance, and with the statistics we use, it seems we can be confident that this seems to be a real effect. That there really is diminished performance in the dim light.
When a spider catches, when a jumping spider catches a fly, how does it eat it? It's not wrapping it up in like a paper holder. So it's just part of it, or how does it work?
Yeah, so that's a good question. They just they grab it with their fangs and they inject venom right away. And usually the prey doesn't even seem to be struggling for very long. I think the venom takes care of it pretty quickly, and then they just hold it in their chelicerae, their little things for several minutes, and then they suck out the insides, and then they leave a thing that looks like the outside of the prey. Some spiders chew it up and it looks like a mush ball, and jumping spiders just suck out the insides, and a lot of other spiders do. Yeah. Right, it's interesting that they are able to take it down so quickly, because some prey is kind of feisty, but I guess their venom does the trick. So one other difference, I also looked for not just the percentage of times that they succeeded, but for the times that they did succeed, how long did it take them to catch it? And this is the average number of seconds that it took them to catch their prey. And it took a lot longer to catch them in the dim light than in the bright light. And so one thing that this also could mean is that usually in the wild you don't have spiders catching flightless flies inside of transparency slides. So this, if it takes a minute and a half to catch their prey, it's likely not gonna happen. So to a certain extent, those numbers from before they're higher than what we would expect to see happening in similar conditions in the wild.
Because normally the prey would get away.
Yeah.
Whereas in this situation, it's captive, right?
Yeah. Yeah, it's captive, and there's nowhere for it to hide. And then in space, no one can hear you scream, and so there's no kind of way for it to get away. So now I'll tell you about the work that I am in the process of doing, which is a continuation on this experiment. And so my hypothesis in Habernatus formosus, which is the name of the species that I'm studying, which doesn't have a common name, which is unfortunate. We're trying to make zodiac spider catch on. So you could call them that. These are zodiac spiders.
Why?
That's the name for them, yeah. Everything needs a name. And so my hypotheses are in Habernatus formosus. One, vision is a primary sense used for prey capture. This is pretty strongly supported from what I did before, but then I'm kind of retesting this by manipulating a few different things. The other is the vibratory sense is also used in prey capture, and so even if the vision is totally critical, it could be that the vibratory sense is providing some extra information that helps. And the other thing is that the sensor demands differ when capturing different types of prey. So as I said, they're not out there catching fruit walks all the time, and so it could be that with different types of prey, we would get different results. So this is what I did. I designed an experiment where it was a 2x2x2 design, so I had 3 different things that I changed, resulting in 8 different experimental treatments. The first thing was that I give them either a fly or a cricket. And the cricket was the more realistic prey I was foreshadowing. And these are, feisty crickets that hop around. They're not bred to be sort of weakling crickets in the way that the flies are. Well, the flies were bred to be weakling flies, not weakling crickets. That would be cool. That's my next project. So flies are crickets. They were the same size, though. They're teeny crickets. Same size as the flies. The second variable I manipulated was I changed the substrate. So I either had them on a stretch stocking, like I did before, or I had them on a stretch stocking but with cement underneath, so that the vibrations wouldn't transmit through the substrate. So essentially silencing or almost silencing any of the substrate-borne vibrations so they couldn't use that to detect their prey with their lyriform organs. And the third thing I manipulated was, like before, I changed the light. So I had it bright or dim. And the dim light was my way of sort of removing the vision, but in a way that didn't make them completely unable to catch the prey whatsoever. So if I removed their vision by making it totally dark, it would be 0 across the board, and I wouldn't be able to get the subtleties of how vibration plays into it. But if I'm able to worsen their vision, I could see to what extent vibration may be able to compensate for some of the loss of visual information. Something along those lines. Yeah? So to measure vibrations in our lab, we use a laser Doppler vibrometer, it's used in engineering things. It's not, but it shines a laser down and then has the laser shine right back into it, and then it's able to. And if there's vibrations, it's able to detect the difference in time that it takes the laser to come back, and use those to measure really tiny vibrations in substrates. So the sound effects from the video I played earlier were taken with a laser Doppler vibrometer. So we couldn't hear the spider song normally, but that allows the tiny vibrations on the surface to be translated into sounds that we could hear. Yeah, it's a cool device. It's cool. thing. So that's what I did, and then, these are my methods. A lot of this I told you already. I only use one spider for each trial, so I didn't have Jerry go in a dim trial with a cricket and then also a bright trial with a fly. I fed them both crickets and flies before the experiment, so it wasn't new prey for them. I made sure that they spent several days not eating so that they were hungry enough. And then the crickets were the same size as the flies, or similar sizes. They're little crickets. And so this is what it looks like. This is the carry, and then there's a fly right there. Boom, fly tiger. You can watch it one more time. It's pretty cool. The nice thing with working with tiny animals like this is it's kind of like also always watching Planet Earth over and over again when I go through this. Because I'm sure if you work with actual non-fly tigers, you don't get to see them eat something every time. But it's cool.
Is the spider crawling onto your little removal thing there, trying to get to the prey before you remove it?
I couldn't say for sure, but a lot of times it definitely seems like it. Definitely seems like they see the prey underneath the thing and go for it, which was sort of all on purpose. I wanted them to know that they were after something. But,
Excited.
yeah,
Do jumping spiders use any chemical cues?
they might. She asked if jumping spiders use any chemical cues. A lot of other spiders definitely use chemicals to either detect prey or find mates or other things like that. We don't know at all if jumping spiders are using chemicals to catch their prey, and that's something I may do down the line is see sort of how jumping spiders use chemical information as even a third sensory modality in coordination with all those other things. Yeah?
What is diurnal spider behavior like in low-light conditions where there is no food around? Do they normally sleep? If they were in there by themselves and there was no prey, would they just torpid? Would they jump around?
If they were in the wild or in my thing?
In your test?
Yeah, so they sometimes, that's a great question. They sometimes jump around. They sometimes just stand there. Most of the time they just sort of stand there. Sometimes they try to get out of the container. One thing that I have wanted to do is have them, is do, 33-minute segments of a spider just standing by itself and then compare their movement and their jumps to if there is a fly to see if they're detecting that at all. Yeah, no, that's also something I've wondered. So that's how I do it. And then what happened with this one? What happened when I had different treatments? I'm going to show the fly one first. Anybody want to guess? I'll just show you because I still need more data before I can make it very conclusive answers to it whatsoever. But this is what it looks like. I used emoji codes for the different types of treatments. The two on the left are the bright treatments, and the two on the right are the dim treatments. Statistically, they did a worse job in the dim light than in the bright light. As far as the vibrations go, the ones with vibrations are the blue and the green, and the ones without vibrations are the orange and the red.
Wow.
So it's actually, and statistically there was not a detectable difference between those performances. So at least for the flies, it doesn't seem like, even though these bars are different heights, it doesn't seem like, they seem within the realm of normal variation of what we would expect just randomly. So we can't, yeah?
Is the vibration in dirt more like that of concrete or like the nylon?
That's a good question. My guess is it would be somewhere in between, but I don't know for sure. They definitely stand in the wild. They stand on some things that they'll stand on rocks, which I'm sure are more like cement, or they'll stand on leaves, which are more like nylon, and they'll stand on twigs, which are probably somewhere in between, and in dirt and different things. So they definitely, in their actual normal behavior, they'll go on to different substrates with totally different types of transmission properties. So at least for these flies, it doesn't seem like the vibrations are playing a role. For the crickets, one thing that's striking about the crickets are across the board for every treatment, they did worse at catching the crickets than at the flies. Not entirely surprising, because they are, the crickets jump around and they've got all their stuff. The flies can't fly, so maybe it's sort of like, not totally fair. It's like the cow in Jurassic Park, where they're a little bit, but the crickets, a lot of the times there's really sort of a thrilling chase with the cricket jumping away and the spider almost getting it. And so crickets seem harder, or maybe less tasty, or maybe the spiders are a little more wary of trying to go for them. And then within the crickets, the light had a giant effect. It was way harder to catch crickets in the dark in the dim than in the light. But with the vibration, there also was no detectable effect for the crickets. So, but one thing that also is interesting, and this is part of it being ongoing, is I don't have enough samples of this to know either way yet. Is if you look at the red bar, this is the crickets in the dim no vibration treatment. This is the flies in the dim no vibration treatment. It seems from now like it may be the case that for difficult prey in low light conditions, vibration may matter. But the nature of science is that it might not matter at all, or it might totally matter, and I'll find out when these spiders come back out this spring. So,
what's your sample size there, and how many more times do you have to do that to get confidence in the answer?
Yeah, so the sample size for this is about 100 in total. There's I think 120 across all of them. So there's about 15 per treatment, and so I'm going to try and do about 300 more, and then hopefully it should pop out and give me a little more confidence in either the ability to confidently say no, this is not happening, or yes, this is. So that's what we're dealing with. One interesting thing that happened with the cricket success rate that did not happen with the flies is that two other things seemed to have an effect, or did have an effect, and that was the day that I did the experiment. Don't know why. I have no idea why that happened, but it was different from day to day. And also the sex that the spider was. And an interesting thing about that, and the female spiders caught the crickets at a higher rate than the male ones did. And I was puzzled for a sec, but female spiders are a lot bigger than the males, sometimes twice as big. And these crickets, as I said before, are feisty. And so it could be that the female spiders were just burlier and able to take down the crickets, whereas the males weren't. Not sure.
Were you surprised by these results? Were you surprised that there wasn't a bigger difference between the vibration versus non-vibration?
Yeah, I thought since the vibration is known to be super important for the mating decisions, I thought that it would also play a role in this, but yeah. This is a mix of females and males. Yeah, so I don't have a graph showing the difference between sexes, but that there was one.
Can I fire off like 3 questions?
Yeah, go for it.
Because females are they more sensitive to vibrations because of the sex habits between the two? And did you see a difference at all between the males and females?
That first one is super interesting, and I have never thought about that before, and that's really cool. The second question, a difference in what?
A difference in the success rate when vibrations.
Like.
I'm sorry, you're talking about the prey, not the predator. Apologies.
Oh, yeah.
Yeah.
But
My bad.
that's it. I mean, it could be that I was talking about the male and female spiders. Yeah. Yeah. No, there wasn't an. I didn't even check for an interaction with vibration and sex, but once I have more samples, I could do that, and that would be super interesting.
Do the males ever like eavesdrop on the other males doing displays and like try to out other males?
Oh, I don't know. Definitely sometimes there'll be more than one male signaling at a female at a time. I don't know if they would be eavesdropping. I think they kind of just trigger their courtship immediately when they see any female they come into. They even will court dead females of a different species, which is disgusting. Not to like put value judgments on animals, but that's gross. Yeah, it's sad, yeah. I mean, imagine buying a drink for a dead chimpanzee. This is not... Yeah, but actually the video that I showed, the courtship video, that was a dead female of another species, like on a stick with like a leg falling off. It was like really good. Like she came from the freezer. Yeah, I like that. So, yeah. Anyway, how long did it take to get them? Oh, sorry, yeah. Oh, yeah, you got it. What?
Okay, really quickly. So do they have a really simple gut because of their diet? Because I know in insects that, let's say, are sap feeders, their gut is highly enlarged because it's so non-nutritional, and insects that eat things that are particulate when they're actually chewing the chitinous bits, like it gets all smashed up in their gut bits, so they have a bunch of like chitinous sides and like crushy bits. And so with spiders, I wonder, is it really simple?
One thing I heard just a few weeks ago is that spiders don't have any gut microbiome, so things go past through them super fast. That's not true. I thought somebody said that. Somebody.
They're actually like take the microbiome of the prey that they're eating. We're doing an experiment right now.
Oh, really? I probably heard it mistranslated from something that somebody heard from your lab. Wait, so what's the deal?
It can be transferred, and then also their gut can go down into their legs. So that's kind of
Ooh, that was the thing I was going to say next. Yeah, yeah, and so it's super disgustingly, I'll say it. They have these gut diverticula that they're like, it's sort of intestines like go into the top of their legs and all throughout their body because they eat so much stuff and it just goes off, and then it gets digested and it goes through.
Really quick. Okay, so have you tried feeding them chemically dependent insects at all?
I haven't. Other people have.
If you're interested in a collaboration with somebody, I know that the Whiteman Lab is they made a mutant Drosophila that now can retain like carotenoids or whatever it is. Anyways, they're chemically dependent mutant Drosophila. She wants to do like an experiment test.
I'm down. Yeah, let's do it.
That seems perfect. Rabbits are too dumb. She asked me for specimens, and he's
Yeah. Okay, that's happening this spring for sure. Yeah. So, how long did it take them to capture the prey? This is the graph. From just looking at the little rectangles, it looks like there's something definitely going on. But this is not. But one other thing about the rectangles is they don't tell the whole story. The black lines are the error bars, so the real value could be anywhere between the top of the black line or the bottom of the black line or even beyond it. So really it could be, this looks like it tells a true story or something, but I won't know until I do more. Anything about what's going on, about how long it takes them to capture these prey under any conditions. And it's even worse with the crickets, because I can only find out how long it takes them to capture something if they capture it. And they did such a bad job catching the crickets that the sample size was even smaller for this, so I'll get back to you next year about this one, but it's fun to show stuff that's in progress, right? This is cutting edge. This is cutting edge. And so, this is the cutting edgiest. And so what did I find? So prey type matters. Definitely matters. The lighting condition matters a lot. So in these dim lights, they really do a lot worse, especially with the crickets. The crickets seem super hard to catch in the dark. And then the vibration may or may not matter under certain conditions, and that's sort of pending. And so looking at my hypotheses again, vision is a primary sense used for prey capture. I think I can confidently say yes at this point for that one. Vibratory sense is also used in prey capture. We'll see. Sensory demands differ when capturing different types of prey. Interesting. We'll see. So why care about all of this stuff? So why am I doing this? One thing is that it could be useful. There are weird, esoteric, and little invertebrate vision research has had some cool translations or effects on technology. There's been a lot of computer vision was inspired specifically by jumping spider vision. Jumping spiders are so tiny and they're able to achieve such complex tasks and have such good vision for their size that it took actually decades of research to be able to get even close to it, and now we still can't using the same amount of processing power and energy as a jumping spider, we still can't have as successful of cameras. We need to have way more energy pumped in. They have to be way bigger than what a spider is doing. So they still have something figured out that we don't. Then also, not from jumping spiders specifically, but so research on crustaceans has recently had medical applications where some methods that they developed for research on crustacean vision is being used. There's a new company being founded that checks for macular degeneration in humans, so they're able to diagnose people's eye problems with things that they use to see how little crustaceans see. Another thing is the interestingness. And thank you. And there's some interestingness on a couple of levels. One is the behavioral ecology of it. It's what these jumping spiders are super successful. There's over 5,000 described species of jumping spiders and probably plenty more undescribed ones. They're the most diverse type of spiders, and there's a lot of spiders in general, as you may have noticed by looking at the world or your house. So jumping spiders really have it figured out. And one of the main things they have going on is these really cool senses, especially the vision. And so understanding how that vision plays a role in their ecology can understand sort of how they were able to hit the ticket in a good way. Another thing is understanding just the sensory evolution, knowing what sorts of factors cause animals to evolve really exceptional senses is interesting. If you ever so I mentioned hawks at the very beginning of the talk, and hawks have the most acute, the highest spatial acuity vision of any animal that we know of, probably of any animal. Large birds of prey, I like to say the most megapixels of any animal. And does anybody know what number 2 is next to hawks? No, nobody said it yet? Huh? Well, including all birds of prey. Yeah. Number 2 animal, second highest spatial acuity. Anybody? Yeah, humans. Yeah, people always when they're watching nature videos, they're like, humans suck. Cheetah's so much faster than you. But it turns out that humans have incredibly high spatial acuity, which is probably why we think these spiders are so cool, because it's a special thing for us. So we really, it matters to us how much detail things are seen in. And it turns out humans' spatial acuity is incredibly high. So why? I want to know why. Also, humans are I mentioned we have sort of 3 color channels. We could see a lot of colors compared to, talk about dogs being colorblind stuff. Most mammals don't have very good color vision. Humans and a few other primates do. What's up with that also? We don't really know, and I'd like to know. And you can't understand that sort of thing by just looking at one example. So looking across all sorts of different animals with different independent evolutions of new sensory abilities allows us to understand better the mechanisms that cause different sensory abilities to evolve in general. So that's another thing that adds to the interestingness. And the last one is just the aesthetics of it, which is thinking about these kind of things or talking about them or researching, you sort of get to imagine what it must be like to see the world through the eyes of a spider, or the weird lyriform organs of a spider. The different animals have different senses, and sort of being able to learn about these things and try to imagine what it must be like to experience the world in such a different way is, I believe, it's an intrinsically enriching experience. Sort of think about how different things that are doing fine can be. So that, I think, is cool too. And so thank you so much to all of you for coming out, to tons of people who helped me collect spiders and give me ideas and help me run experiments, and are my friends or raised me. So yeah, I've got a lot to thank, and and thank you for coming out, and thank you to organizers for doing a super amazing thing. This is a cool thing, and thanks for Scarlet City for hosting this. This is wonderful, cool pinball machines I can't wait to play. And so thank you all. Yeah. If there's, does anybody have any last questions or anything? Yeah.
I do. So the last couple charts that you had, the red bar, it was dim light and then the vibrations were low. Was that on concrete? It was a line on concrete?
What was it? These ones?
The last one, yeah. So everything with the red bar on it, all of your graphs.
Yeah.
The speaker icon is a line to it.
Yeah. That's concrete.
So in your test environment, it was concrete, it was nylon on the concrete, so it was less vibration, right?
Yeah.
So what I was wondering is, I guess the difference between the fly versus the cricket. So did the crickets stop taking vibrations in between when they weren't moving around, and the flies were kind of having more constant vibration while they were?
So I didn't measure the vibration for each trial because that requires shining the laser in, which introduces new light and stuff. But I have been looking at how much time each different prey type spends moving in the different trials. So which sort of gets at maybe what you're asking. If
I was just wondering if flies are basically easier to catch because they're making more vibrations more constantly versus the crickets. Because the crickets maybe they're more erratic. When they're not moving, they're not as vibrating.
Yeah, I'll know super soon which ones spend time moving. As far as how that translates to vibrations specifically, I don't know that yet, but that is something I could. Now that you met that's a good idea. I'll look and see if they do different amounts of vibrations. The crickets also do walk around a lot, so they're also just walk. In addition to jumping, most of the way they move is also by walking, similar to how the fly does. I don't know if they walk in a way that has a different sort of vibration pattern, but I could look at that, and that could be cool. Yeah, maybe. I didn't hear, well, I guess other than the sounds of them walking, I didn't hear them sort of generating any kinds of sounds, but that would also be really cool. I could figure it out. Yeah, I'll shine the laser on them and see what happens. It'll be cool.
They're not really flies, right? They're walks. So
yeah, right. They're walking.
Making that vibration with their wings, right?
Right. Yeah. So a real fly, a regular fly would make. Yeah.
How are you with field IDing all these spiders? I feel like it'd be really hard. Like, do you need any genitalia to tell the species?
So no, because luckily there are some species that look super similar to the species that I'm catching, and there are some places where both of those species are there. But at Lake Berryessa, there's 4 or 5 different species of jumping spider in the same genus as the one that I'm catching, but they're distant enough that I could, and anyone here could tell the difference between those after being shown a few examples. So you luckily don't need the genitalia for those. I had another joke or some other important. No, it wasn't a joke. So Ashley and Natalie made these very cool spider goggles. So I mentioned the anterior median eyes they have like a really narrow field of view, and they can be controlled independently. And if you want to know what that's like, you could put on these cool things and see through the eyes of a spider. They're sophisticated. So yeah, if anybody wants to try these, yeah. You wanna? Yeah, it's not.
So if you like,
Yeah.
I was going to say it's fascinating that it appears that you have found, that they really just use their vision so much more than vibration, whereas web spiders, like Charlotte's Web type spiders, really don't use their vision at all and only use the vibration. And so that's really, it's so drastically different. That's really curious and fascinating.
I absolutely think so too. It's so cool how they could transition their sensory needs so drastically. It's awesome. Yeah.
okay.
Yeah. Thanks. Yeah.
Thank you very